Good afternoon, everybody. And thanks very much to INCIBE for inviting me to participate and to make this presentation playing police and thieves to detect anomalies in the network and in the internet with machine learning. My name is Carlos Torrano. I hold a PhD in computing. I studied at the Universidad Carlos III de Madrid. And I've done my PhD work in artificial intelligence and the scientific research board and the so-called physic in Spain. I currently work as a senior researcher in 11 Paths, which is a Telefonica Cybersecurity unit. And there you have my contact details in case you want to email me. What am I going to talk to you about today? We're going to talk about many things and also about machine learning, which is very much a topical issue these days. And you probably ask yourself, why? Why are we talking about machine learning so much these days? One of the reasons behind this is because we live in a world full of data. We're overwhelmed with data. We have IoT, we have sensors deployed virtually everywhere. We have the wearables, we have the watches, we have our smartphones. Even home appliances have sensors, cars, everything, virtually everything will be connected. And this translates into a huge amount of info that we will have to process and store appropriately. And it is here where it's very important that we talk about big data. And all of this needs to be duly processed. We need great computation capabilities in order to process all this information. And it is here where machine learning will play a role. We can use ML techniques to process huge amounts of data because human beings alone cannot process them. We don't have the resources, capabilities to manage such a huge amount of data. That's why we need machines to give us a hand and to help us process data. The goal of my presentation is to introduce you to the world of machine learning, tell you how it works, and for you to understand how we can apply machine learning and how we can start using machine learning algorithms. There are several or multiple applications to machine learning, and one of them, which is well known, is anomaly detection. If you allow me, this would be like looking for the red egg, spotting the red egg among all the white eggs, i.e., to be able to detect something that stands out. We can profile what we understand by normal and what commonly happens, and then try to detect anomalies. We can detect malware issues and all sorts of anomalous behaviors. Even a Black Friday could be an anomaly. To do so, as part of anomaly detection, I'm going to focus on anomaly detection in network or web traffic. And we have IDS and IPS devices, and these are systems for the detection of intrusions. And I'm also going to talk about WAFs that work at an application level. How do they work? They are basically positioned between the customer and the server that we want to protect, and basically what these systems do is monitor all the traffic. So when an anomalous behavior occurs, it can be detected. Let me continue with metaphors. And as I was saying, these systems would be like watchdogs or policemen. We have many police officers here in this venue, and it's almost like a bouncer. These people are trying to see or are on the lookout for the good guys and the bad guys, where the bad guys are to stop them, or where the good guys are to let them access, almost like a traffic officer or agent. Good. These systems can be classified in many different ways depending on different variables, among them functionality. On the one hand, we have the IDS, and the IDSs issue an alarm or an alert whenever an anomaly is detected. An alarm is transmitted. And the IPS act in a more proactive manner. Basically, what they do is interrupt traffic whenever an anomaly is detected. An anomaly, the traffic, sorry, is kept, and this can be useful in some cases, but it can also be problematic in other cases. And then we have the systems that protect the specific host and the NIDSs that protect the traffic circulates through the net. And the other classification that exists is based on the approach adopted. We have the signature approach that has been used commonly during the past years. Basically, it collects the known malware signatures, but the problem we are facing here is of a different nature. Problem is that these don't adapt well to variations in anomalies. For example, whenever we have mutations or when there are new behaviors that are not registered in the form of signatures and therefore go undetected. Considering the great amount of variability, it's very important to be able to react to all these threats. And to do so, we have the so-called anomaly approach, which is a positive approach because what it does is to define a profile of normal behavior, and all deviations or diversions are considered to be anomalies. This allows us to detect all those unexpected behaviors that hadn't been considered in the past with the signature approach. And we commonly use machine learning tools when applying these approach. Machine learning algorithms work very well in detecting patterns. When we want to detect patterns in data or patterns in behavior, you need to understand that these algorithms have been designed to identify patterns, to characterize them, and to detect all deviations or anomalies from these defined patterns. On this slide, I have wanted to explain to you the process followed to apply a machine learning algorithm to solve a specific problem, in this case to detect anomalies. So here you can see the different steps to the process that need to be followed. First, we have a data set, basically the ensemble of data that we're going to use in our system in order to feed the system, and these are the data that we're going to analyze. And it can be appropriate perhaps to have a pre-processing stage regarding this data, and then we will extract or the features. So what we do is extract or characterize all those features that will allow us to profile the normal behavior, and therefore this will allow us to detect deviations. At this stage, the work of the analyst is very important because he or she will help us know what features characterize normal behavior as opposed to unexpected behavior. And in some domains, it's very important to have the expert knowledge or expertise in that particular field. You need to consider that there can be highly complex problems with many variables or features, and in terms of computational performance, this can have a negative impact on the system. To streamline this, we can select some features, i.e., we can choose those features that really provide relevant info and that are not redundant, that don't disturb us, so to say, so that we can make this process much more agile. Then we move on to the training stage, when the algorithm learns. It's like when we human beings read a book or study a book and we learn. We acquire all the knowledge required regarding what is normal, and that's when we extract all the patterns that will help us characterize. And then we move on to the test stage in order to verify and check how well our system has learned this and what the capabilities for the system are to detect unexpected behaviors, unseen behaviors. And last, we conduct a results analysis to know to what extent the algorithm has been accurate in the detection of anomalies, and we can even consider reiterating and fine-tuning the stages in order to be able to improve the results if needed. My presentation is divided into a series of sections, and I'm going to try to analyze in further detail the components of this flowchart. So let's begin with the data set that we can want to use. This in itself is a challenge, at least for the time being. I've included this quote from authors that say that the most significant challenge that an evaluation faces is the lack of appropriate public data sets for assessing anomaly detection systems. So we need to have public data sets that are labeled, and that is very costly. It's very difficult, and we need to consider that data sets will be essential because this will be what will feed the algorithm. So we need to be able to work with adequate data sets. This is a table that I prepared for my research, and I extracted the parameters that the data sets should have. Well, they can be public or not. This can be convenient if we wish to compare different systems. If we're going to use supervised machine learning algorithms, it's important that they are labeled or having updated attacks, because some of the data sets are criticized because they have very old attacks that don't really help us assess systems well effectively. So there are some data sets that are out there that can be used, but as I was saying, there are always some drawbacks, some pitfalls, some inconveniences to them. So one of the options is to use the existing data sets. Sometimes what happens is that they have synthetic data, and another option is to create our own data set. Data sets, depending on the layer we're working on, could be HTTP if we're in the applications layer, or we can work at layer 3, i.e. network traffic. We can even work on traffic statistics considering the high volume of data in a network. NetFlow is a protocol, a commonly used protocol for the detection of anomalies in network traffic. It was developed by Cisco in 1996. We're currently at version 9 that's specified in RCC 3954. NetFlow basically collects or compiles data regarding IP traffic when it enters or leaves the interface. It does stats. It defines how the router exports data. There are many different fields in NetFlow, but I've brought some for you to see and understand what we're talking about. For example, data regarding the date and hour of the beginning of the flow, destination, IP, ports of origin and destination, type of protocol, the interface, and the bytes or number of packages, both incoming and outgoing. These are some of the data with which NetFlow works. In this case, we have working with, let's say, gross crude data. And this has pros and cons, as we will see shortly. These systems have three main components. First, we have an exporter. Basically, what it does is aggregate all of these packages in several flows and exports these packages to collectors. And the collectors receive this data and store it. And the analyzer then analyzes this info using the processes that we have defined. Pros of using NetFlow instead of, let's say, traffic as it stands. Well, it's light, it's universal, and it's adopted as a standard in many devices from most important manufacturers, among them Cisco, Jupiter. They have all integrated NetFlow. So it serves this purpose very well when talking about putting into dialogue different devices. One of the main advantages of NetFlow is how they abstract from details. If we consider the huge volume of data that can circulate through a network, it's very hard to see what is happening. So, in a snapshot, very fast, you can see and analyze what is happening in the network. For example, if it's used in a strange time of the day or there is some sort of attack. With NetFlow, we analyze all this data and we are able to detect this very easily. And aside from this, it can help us regarding privacy or confidentiality issues to make sure that no personal data are disseminated. And we believe it can be useful to flag alerts in level 1. But thanks to this detailed abstraction, well, this is an advantage, as I said, a pro, but also a con or a disadvantage, because in NetFlow, we would be missing a great amount of info and some attacks. If they can only be detected with the application layers data, they would go undetected this way, and we wouldn't have sufficient information or data to detect them. So it can be useful in some cases to fine-tune this with DPI, with a more detailed inspection of packages, or sometimes with the features of the applications layer.
Un dataset que sea existente, o podemos también fabricarnos el propio. Si optamos por esta opción, necesitamos...
Now, if we choose this option, we will have
lo que llamamos
legitimate traffic, which is background, and then we need the anomalies that will be detected. So we're going to see how this is implemented. I'm going to focus now in the legitimate traffic in a network that is free of attacks. We would do it with the following scheme. Based on the switch, we would do a mirroring of the traffic, as is the case in some IDS, and this will send the traffic to the NetFlow proof. Then we can send NetFlow traffic to a device in the cloud, and then we can start the data science and machine learning process.
Y bueno, luego por otra parte necesitamos también lo que es el malware o la...
Then we need the malware or anomalies. One of the options is to use real malware samples in a controlled environment.
Disponemos de esto.
If we don't have these samples, another possibility is to download some, as you can see in this screen. The name is Malware Traffic Analysis. I don't know if you know this web page, but it has a dated structure that links different types of malware, explaining how it can be detected or the anomalous behavior, and the tech-ups can be directly downloaded from this website. This could be a source of information to get the malware in order to test our system. This is just an example of downloaded malware, pseudo-darling, and it's a group of malware that finally starts a ransomware. If we open the page with the words that the traces of this malware flow indicates that from the same IP we have consecutive destination IDs, which give us a clue to detect the malware and to set the features that will allow us to detect anomalies in our system. So an analyst, when seeing this screen, could see that it's not a normal trace of the net's flow or traffic. These consecutive IPs happened in only a second. All of this is data that can be used to set the system's specificities. In the pre-processing step, we might need several actions. For example, making data anonymous, erasing some null data that can interfere with the algorithm, and also discretization. Some of the algorithm cannot work with long streams or with alphanumeric chains, and we need to do the conversion into numeric data. Behind the machine learning algorithm, we only have numbers and mathematics. It's not magic by all means. In this step, we would get features extraction that will allow us to see what's normal from what it isn't. And in order to illustrate the importance of this, I present you a quote by Pedro Domingos, a researcher and a professor at Washington University, that says the following: at the end of the day, some machine learning projects succeed and some fail. What makes the difference? As researchers or experts in those areas, sometimes we wonder what makes the difference, what made a process successful or a failure. His answer is that easily the most important factor is the features used. This is what will allow us to learn with the algorithm, being able to distinguish an attack from what is not. It's also important to highlight that during this stage, most of the effort is devoted. Around 80% of the project's effort is invested in the data science stage, everything related to data manipulation, fine-tuning, fitting, extracting the necessary columns. So this is a very important step, therefore. Now, in order to extract the features, we should take into account different factors. Here, the analyst role is essential, and there are a few things that give us information about where can we start detecting anomalies in our net. If an element communicates in a very brief period of time, communicates with many different public IPs. On the other hand, if we're working at a more detailed level, we should take into account the URL length and structure. We can see if they have run files. Many of the malwares download exe files. We can see whether there are anomalous parameters that are important to take into account in relation to attacks, and we can analyze the parameters of the URL with one of the proposals we made in a paper. Take into account the characters distribution and the rates of letters, digits, and non-alphanumeric characters. That will help us to differentiate between an attack from what is not. Those are just a few examples. After our features extraction, and depending on the problem, some of them are very complex. We speak about hundreds of features. We need to select the most important ones, those that are really relevant and provide information to sort out our problems. So everything that is irrelevant or redundant or might have correlations is not needed. We have to erase it to improve our performance. When we don't have to process such a huge amount of data, the algorithm will work better, and in some occasions we can just play and see what happens with the results. Here the challenge is to know how much we should erase. If we erase too much, we might not sort out the problem. So we should see when to erase and what are the core features that will provide the solution to our problem. So the challenge is to have the fewer number of features that will allow to sort out our problem without impacting to our results. I've seen cases where the algorithm properly functioning help us to improve our results, so it would be a win-win. Those feature selection algorithms are of three types. First, the wrappers. They use the power of a classifier or to see whether a feature should be included or not. The drawback of this type of algorithm is that they are less efficient and need more time. Those that are based in filters, they are independent from the classifier. They use different techniques and therefore consume less resources. And thirdly, the hybrids that will be built during the training stage of the classifier. They are middle way between the two. First, about the ML algorithm, there are many. It's incredible. I discover new ones every day, and the whole field is very interesting. There are different types. Here you have some of the best known as the K nearest neighbors, SVM, decision trees, redes neuronales, clustering, isolation forest, and therefore a wide range of algorithms. Each work differently, and they are based on mathematical criteria. When we speak about machine learning, how to make machines to learn, I'm sure you've seen or heard about supervised and non-supervised algorithms. Those that are supervised are used when we have a label for our data group. That means, or data set, when we're detecting anomalies. If we have the network traffic, we might know, either because it's done by a human or by any other means, we know the classification or sorting. We know there is something common in the network, or if it's an anomaly or malware. If we don't have the label, then we go to non-supervised algorithms, those that without this previous knowledge can help us process the information. Now this graph about machine learning algorithm is here in this presentation because we might think, where do I start? I don't really know how to do it. So I thought that this graph was quite interesting in order to give you an idea, I don't know, on the first sight, to know what you should do. First is to choose a machine learning algorithm that is from Learn from Python. First we should see the number of samples, and depending on whether we're gonna work with categories or with quantities, we would be at a regression approach or classification one. And there are different algorithms, there are different criteria used, but here you have a few examples. Then depending on whether we have the labels or not, we would be working with labels, or we can use clustering algorithm that will Kamins, for example, is well known will allow us to do the sorting without the labels, or we can use size reduction algorithms which are related to the feature selection. Among all machine learning algorithms, I will speak about one in particular. It's quite new, and the name is isolation forest. This is a non-supervised algorithm usually used for anomalies detection. To detect all those anomalies is proven to be quite good. We're gonna see its structure in broad terms. The main idea is that anomalous data are easier to isolate through the recursive partitioning of data sets. We choose at random one of the variables of the data set and also randomly some limit values, so the data set becomes divided. We have different lines that will divide the data set in two parts. We might end up designing the tree to your right. On a second round, we will build the second line or use the second variable in such a way that we can build the tree. It's based on decision-making trees. When we make the partition of the data set, we see that A, that was an anomaly, was isolated, and is based on the idea that anomalous data are easier to isolate than normal data. Normal data will require a higher number of cuts, and based on the depth of the tree that makes reference to the number of times we've divided, we can see which parameters are anomalous or not, and then we will use some other processes as contamination. Then we get to the training stage, when the machine learns, when the algorithm with all this information starts learning about the model that will allow us to predict data. This is the stage before the algorithm starts detecting, before it's in production. Once all patterns are incorporated, we then go to the test stage, when the algorithm is already detecting the net's traffic. And as I said, as a police officer, those that have a positive pattern can go, and we isolate those that not. What we do here is to analyze cases that haven't been visible before, not to analyze the same data that we've seen at the training stage. What is interesting of those algorithms is that they have the capacity to generalize, so to detect data and anomalies that were not seen before, and this is their strength compared to signatures approach. Here is where we see the algorithm's predictive capacity. We should be aware of not over-adjusting things. This can be seen in this drawing, where we might have data of the blue and red class. The green line, if you see, distinguish them and adjust to the data. But what is the problem here? When we have a data set that is slightly different with unseen data, the algorithm might make mistakes in the prediction because it's been over adjusted to a specific training model. So when new data arrive, it will not have enough generalizing capacity to detect anomalies in a set that is not exactly the same as the one used during the training stage. And here we have to see that the algorithm should learn and make generalizations in the right way. Another stage is cross-validation. As I said, what is interesting is to have the capacity for data detection that had been previously unseen. And to avoid over adjustment, we have to divide the data set in two parts. Part of the set is used only to train the algorithm and the other part to test it. And the evaluation is about data that hadn't been previously seen. Another approach is to use validation data, divide the data set in three different sets or subsets. And here is the CAFOld. We have the CAFOld cross-validation. Is a technique used to give more reliability to the evaluation stage. As I said, the data set would be divided in different subsets, training and evaluation, but this is quite random. In order to avoid bias in our classification, we have to repeat this process an n number of occasions, especially k number of times. What would we do? We divide the data set in k number of different blocks. All those blocks minus one are used for the training, and one of them, here the yellow one, would be used for evaluation purposes. In the next round, what would we do? We might use the next block, and through iteration we'll be using the following block for validation and the rest for training. We might repeat this process until completing the k number of iterations. This gives more reliability to the results. Once we've carried out this process, we can go and analyze our results. Depending on the labels and the results provided by the algorithm, we build a contingency chart with false positive and false negative. Here you have a visual representation in this chart with ticks and crosses, green ticks and red crosses. Depending on those values, we can build or design different metrics to evaluate those systems. We have accuracy, recall, many different measures can be applied to the system, and we can see how accurate is it. We are evaluating its capacity to detect new threats. Another system is the drop curves. Here in the x-axis, it will be the rate of false positives, and in the y-axis, the rate of true positives, so that you can see it in the graph. False positive rates has to be really low. They are false warnings or alarms in the system, and the true positives, the anomalies themselves that are being detected, we want them to be very numerous, and we can draw a curve as you see in the graph. The closer to the end of the graph, the better results we might have. Way to measure this is using the area under the curve. We might calculate the area below this curve, and as I said, the higher the better. The higher the AUG, it'll be the expected result. In this slide, I wanted to present information about a study conducted by researchers, giving reasons why machine learning, especially for anomalies detection, and in this particular case, and for data traffic, is more complex. Machine learning can be applied to a numerous number of fields: biology, healthcare, business intelligence. But what they say is that specifically in this area, there are specific circumstances that make machine learning more complex. They are more difficult than in other areas. First, due to the high cost of errors, we should take into account that when this type of algorithm is not detecting an anomaly, we can have serious consequences. For example, an attack that is unnoticed. This week I had a meeting with some partners, and they told me how they use all those techniques in an industrial context, and let us think what might happen in an industrial plant if the algorithm does not detect an anomaly that is taking place in the plant. The cost of these errors might be very high, so it's very specific. As I said, there is a scarcity of training data related to the difficulty to have the right data and data sets to test the system. Of course, how different the internet traffic is, they all have many different variables. We have many different protocols. Each of them has its specificities, and therefore there can be different simultaneous events in the net, so it's difficult to describe what's going on in the network, and even more difficult when we want to detect anomalies. There are also difficulties at the evaluation stage, for example, interpreting the results or understanding what that type of attacks our system can detect. We are on occasions very ambitious. We want to have a system that might detect all the attacks, but maybe we can become more specialized. And I will now move to the practical part of my presentation. Everything I've introduced can be done in an easy way in Python. We're going to use two libraries that would be very useful. One is Pandas for the data science and data manipulation process, and then scikit-learn from machine learning algorithm. Pandas is a library that will provide different tools and data structures that will allow us a high performance. This is important when we want to have a real-time analysis. Then we have the data frame class, useful for data representation and data manipulation, and it will allow us to load data from an SQL file or other type of formats. Then we also have scikit-learn that provides different machine learning algorithm, and it has API with the estimador, which is the particular algorithm being used. They have different methods and IP parameters or settings, but usually they provide a training method. In this case, the name is fit, that sets the status of the estimator based on the data, and then the predict data to predict unknown data. So if we do a summary of what the steps of the process would be the following. We might choose the model we want to use and select the hyperparameters and adjust them for this specific algorithm. After, we would extract the matrix with the features and the predictive vector. We will adjust the model to the training data, and then we will finally predict unknown data. Here I will speak about something that is more specific related to implementation, and I would like to speak about pipelines and transformed. This is not well known, and it might be really useful, especially for the implementation of data transformation or data science. I urge you to use those pipelines so that you can experiment and explore, and your life might be easier. To understand about this, I will introduce them now. Pipelines is a sequential list of transformed features with a final estimator. They carry out data manipulation with feed and the transformer. I will show you more specific details later on. To speak about some of the advantages of using pipelines and transformed ones. First, we can group everything. We don't need to go one by one executing them. If we have a huge group of transformed features in the data science process, we can do or use it as a single block. If we wish to add new features,
hacer errores o hacer algo que fuera demasiado repetitivo.
it will allow us to avoid repetitions. It can also simplify the code's reading, making it more reusable and making the execution stage easier. Before showing you the rest of my presentation, to show you some examples of how can we implement this in Python in a rather simple manner, so that everything that I've mentioned, you see how it can be implemented, and what I said is not so difficult, and I urge you to test it. This is a notebook in Jupyter, is present in Anaconda, but you can use any other method. First, I import several libraries, and first I build the data set. I selected the malware, the pseudo Darlich, and I will mix it with the legitimate background traffic that was compiled from internet. I'm speaking about NetFlow. This is where everything I told you starts being meaningful. Once we have our data set together with the data traffic and anomalies, this is a very simple example so that you can see its practical use. The real life is more complex. This is just an illustration of what I've introduced. Once we have our set with these library pandas, we will read this CSV.
Pues vamos a leer el CSV.
We're going to read because we're using NetFlow, we're going to choose the columns we have in our file. Date and time of beginning of the flow, and flow time, origin, IP, destination, IP, origin, port, destination, port, the protocol, plugs, packets, and entry bytes. In addition to this, I've added the label. Here the name is type, because I'm going to use a non-supervised algorithm. We might not need this tag, but I've included it to see and analyze the results and to see if my algorithm is really working well in detecting anomalies. If we introduce this information, this is what we get. Here we see in different columns the traffic and data compiled. We see TCP, port 80. After we will start the data manipulation process, data science, and features extraction that we will use in our algorithm. To that aim, one of the first things we have to do is to group the flows depending on the frequency. Those flows that might have different time rates can be grouped in 5 seconds intervals in this particular example, so that this example is devoted to malware detection. So based on a certain origin IP, it was connecting to many destination IPs in a really brief period of time, so I group those flows by time intervals. Once I do it, we see that the flows that are now grouped in 5 seconds flows, they go from 11, 0.5, 0.10, 0.15 in 5 seconds intervals. From now on, we will start extracting the features. Here I've used the one I mentioned to detect malware, and we do different groupings by IPs, by origin IPs, destination IPs, and all of this would be data manipulation process, and we might end up with a count column that is counting the number of flows during this time interval with a certain origin and destination IP.
Esto sería posible hacerlo así, como habéis visto.
It would be possible to do it this way, or alternatively, as I was saying earlier, we can do this using pipelines. We've defined an estimator that is going to use the pipeline. Then what we do in the pipeline, a set of transforms. The pipeline is like a sequence of transformations in data, i.e. manipulations in data. As you can see here, what I'm doing, well, first I order the index, I group flows in 5-second sequences, the index is reset, then we select specific columns with which we're going to work that have to be numerical for this isolation force algorithm, and last we eliminate all the columns that we won't have to use. This is a very simple, straightforward example so that you understand the role of the pipeline. Instead of doing all these operations separately, I group them together. As an estimator, I will use isolation force with 100 trees and a contamination value of 0.11. Basically, these values sets a threshold, a cap, between anomalies and normal situations. It's the threshold level, and 266 samples are used. After this, what we do is divide and separate data from tags or labels, and then I apply the estimator. To do so, first fit. First, I train the algorithm with the training ensemble. In this case, I've used X, the ensemble of data, but this isn't the most appropriate option. It'd be better to do this with cross-validation, as we will see. So once the algorithm is learned, we predict or forecast the new data, i.e. the assessment of the algorithm. And this yields the following results. For each of the flow lines, we will have a 1 if it's normal or -1 if an anomaly has been detected. This way, we extract the metrics regarding the performance of the system. I have the false positives and the true negatives there, and there you have a list of results. These results are pretty good, are acceptable, but we need to consider that I've been working with a very reduced or limited data set. and reduced time. In a real scenario, we would have to adjust this further in order to obtain good results. A couple of things I could add. On the one hand, the selection of features or characteristics. In this case, I've used a classifier, extra tree classifier to be more exact, and I select some specific characteristics instead of using all. I use a more reduced set of characteristics or features. And we would do the same, fit, predict. And in this case, you can see that the results, well, we've detected the malware, by the way, and the results obtained are slight decrease, still pretty good, but the selection of characteristics or features has reduced significantly the number of characteristics used, which is good in terms of efficiency, but it has reduced the results slightly in this case, so it's worth the effort. But there are some cases in which even if you select features, the results can improve. So keep an eye on this because this can happen. It can be interesting. And for you to understand cross-validation, I'm working here with a group of digits, and I wanted to show you that normally what we do is not to train the system with all the set of data and assess the entire system, but divide it. So to do this, I use the split feature that divides the whole ensemble in training data, 70% and 30%, which is this O.3, which means that 30% of the data set will be aimed at assessment or devoted to assessment. We're using the K-neighbors algorithm, and what we do is the fit with the training data exclusively and predict with test data. So we've divided or split the data set, and the results obtained are more trustworthy, more reliable, and will more accurately assess the capacity for prediction of the algorithm in face of unknown data. And we can apply k-fold or cross-validation here. I'm applying it here with a 10-fold, i.e. divided into 10 blocks. And I've also used different estimators to see the results. And in this case, we see that KNN is the one that provides us with the best results. And I have to finish off because I guess you're hungry, and I don't want to take too much time from the person that is going to take the floor now. As a conclusion, what can I say? The selection of the data set is very important. It's very important to work with appropriate data, and this is always easy to do. As for data size, manipulation, extraction of features, that's a very important part of the project. You need to pay special attention to this because the results you obtain will depend largely on this, and this can consume around 80% of the time of the project. So you need to devote a great amount of attention. Training is also very important, because that's when the algorithm will learn and determine the prediction capacity. And when we're talking about large-scale projects, it's advisable to have different types of experts, to have a multidisciplinary team made up of analysts that help us extract features, also security experts, also data scientists, because the fields can be very different, and maybe a data scientist from the biology world has no security knowledge, so it's very important to have different profiles. Even developers, people with machine learning knowledge, And I urge you to try this out. It's not that difficult. You can play around with this and learn. And without further ado, I'd like to thank you for your attention. And I'm here at your avail if you have any questions or queries.
Hola. Sí, quería preguntarte, ¿hay alguna herramienta en la...
Are there any tools in the cloud that we can use to send the net flow? To do something similar to what you've described? Free of charge if possible? There are several that can be used. Some work pretty well and not free of charge. NTOP is one of them. It's a paid tool. And it's interesting because it has many plugins. And this allows us to capture net flow that has many setting parameters that are very interesting. It also allows you with plugins to obtain features from the application's layer, HTTP, DNS, etc. Since you're asking for something for free, there are other options. For example, NFKD, soft flow. I can give you later the list of tools that you can use for the proof and to be able to extract traffic statistics. Thank you. Well, you have no further questions. Thanks very much for being here, and I hope